All right. Today I'm going to talk about this Leetcode problem. Largest plus sign. It's Leetcode 764. It's a given. It gives basically a grid that is mm, shown by n. Basically, you have a n by n grid. A 2D grid is filled with ones, except for places that are specified by this array mines, which are 0. And it asks for you to go and search in the 2D grid and find the longest possible plus sign, basically, or largest plus sign. In simple word, if you see these examples, you have a bunch of zeros and one. So basically, it's a 3 by 3 array, includes just one at the center, and that's why it's order one, because there's just one, right? And here, for example, the mine array would be 0, 0, 0, 1, 0, 2, 1, 0, 1, 2, 2, 0, 2, 1, 2, 2, right? And so for the other example, you have order 2 because it's counted. You have a plus sign in the middle, and it's 1 and 2. So basically, each direction, starting from center, you have two ones, including the center. That's important to note. And for the last example, you have this one, which starts 1, 1, and 1. And if you go to left, 1, 1, 1. If you go up, 1, 1, 1. If you go down, 1, 1, 1. So it has three ones starting from the center, not center of the 2D grid. Center by center, I mean like a 1 in the 2D grid. So for example, here you have a 1. If we assume this is the center, you have order 1 because there is no other one around this one. Basically there is one here, but it doesn't count. We need to have equal number of ones in four sides, right? And the last example that's shown here, actually the last three, so n is 1. You have a n by n grid, and you have mines which has 4 2, meaning the index, the row 4, which is the last row here, you remember it starts from 0, and index 2, which is this one, are 0. And you want to find the longest the largest plus sign, which is shown here, right? It's order 2. Note that this is not the only, is it the only one? Or yeah, probably it's the only one that has, or maybe not. You have this one here, order to, yeah, this is not the only one that you have here. Similarly, here you have an 2, which is 2 by 2 grid. You don't have any mine, so basically you have a 2 by 2 matrix, all ones, and the order would be 1 because you don't have a 1 that are surrounded by more than basically one arrays. For example, in this example, the array would look like something like this, right? So whichever of these ones you consider, the longest you can get is basically, the longest you can get away from that one is 0, right? Because for example, if you consider this one, you have a 1 on the right, you have a 1 in the bottom, on the bottom, but you don't have a 1 left and up, so the order is 1. Similarly for all of them. And the last one is the similar, you have just 1 1, but the mine says you have 0 at the index 0 0, which basically makes this one 0. That's why the order is 0. So I would like to walk you through the thought process of how we're going to deal with this problem. So basically, you have a 2D array, and you want to see what the largest plus sign, right? So if you think about it, if you go and find each of the ones in the 2D array and expand in four directions, right? Let's say you have a 2D array like this. Let me copy and paste this here, right? And then you go, start from here, you go, and this is not one, so it doesn't count. Go, 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 go until you get to the first one. When you get to the first one, what you do is basically to expand in four directions, starting from here. So now you have order 1 already because you have 1 1. You go to the right left, bottom, and top. And for each directions, you find the longest basically count of ones, right? And the minimum of the all four directions going to be your largest, basically your order of plus sign centered at this one, right? And then you keep moving. So let's say we got here, we found the order one for this one, we move forward, we get here. We do that analysis again, expanding four directions, top, right, left, and bottom. If you go top, we get or another one, which makes it order two, but the right and left, there is no one. So it's in the right side, it's orders one still. On the left side, it's order one. On the bottom, it's order basically four. The minimum of all four would be basically one, right? Because left and right doesn't have any extra ones. Keep moving, moving, moving. Let's say we get here, right? This is basically our new center. At this center, you find the basically the lengths of ones at the top. One, two, three at the top. So that's pretty good. We have order three to the top. And then we have one, two, three. Okay, we have order three to the right. And we have one, two, three. We have order three to the left. One, two, three. We have order three to the bottom, which makes this matrix order three. And that's the idea we're going to use. Basically, if you want to, although this method probably not going to work, but what we can do is that we go around our 2D grid. When we see a 1, stop and expand and try to find the longest, basically the largest plus sign that we can see. In order to do that, I'm gonna basically um, change this minus array for to basically array that I call bands. Just to note that this is the example on the solution tab, so this is not something I made up from scratch. That's the disclaimer. So you can make this array band that basically saves each mine in this mines list as a tuple, right? So this way, because what we want to do, we want to do a lookup later. So let's say if we get to an index, we want to see whether it's in the band or not. If you save it as an array, it's going to be O(n) time to look it up. But what we can do is to save it as a basically hash set or hash table or whatever you want to call it or dictionary, right? This way the lookup would be ordered constant time, and that's much faster. That's what we're going to do. Let's say we have our final largest, basically the order is what I'm going to return later on. I call it res, and I start at 0, and then I'm going to return res at the end. And what we talked about is that you go over the array. Let's say we go over the array, right, for column in range n again, and then we initialize a value k. The k is basically that expansion value I talked about, right? At each r and c, you see if you expand it in all direction, what's going to happen, and if you what order you're going to get, as you can see here. So now we are going to introduce a while loop. This while loop is basically that expansion part. These two basically for loops, the nested for loop goes over every index of the 2D grid, right? We have a 2D grid. And then this while loop that I'm going to write here is going to basically try and expand in four directions and find the maximum number of ones in each direction and then mean all of them so that we get the order for that specific R and C. So we're going to define a while loop which varies between n minus k. Okay, I'm going to explain why it's like this. C n minus k, right? The reason we do this is that let's say you had our index R and index C, right? The k starts from 0 because once you are at the index and that index, let's say in the grid, if you are at the index and that index is not in the band, right, which means that it's 1. And because it's 1, it's already order 1 by itself, right? And you don't need to care about this, about the four sides of it for this while, for the first step of a while. I'm going to write it down. I'm going to explain probably a little bit better later on, because this k comes into the play and becomes important once you, for example, have more ones around, and not just one. Yeah, it's a lot of ones in one sentence, but anyway. So if we have this condition satisfied, what we can check is that we see whether uh, basically we can expand in 4 directions, right? So we go r plus k now, plus kc not in band, and r c minus k not in band, and r c plus k not in band. Okay, and then that's all. What we wanted, this is basically the key part of this solution. So let's forget about this while for a while. What we want to do is that we want to see, right, how many at the index we are in. Let's say we are at index r and c, which is a we don't know if it's a 1 or not. That's why you start k from 0, and when you start k from 0, what happens here, you first check whether r is between 0 and n. That's, it should be, right? The index cannot be out of this range. And you do the same for c. And then when k is 0, it's basically this is r and c, this is r and c, this is r and c, and this is r and c. Basically, you check 4 times. This is not necessary for this for the index R and C, obviously, but it becomes necessary when you want to expand in 4 direction. So when k is 0, for that index R and C, you check whether it's in the band or not. If it's not in the band, means that it's 1, right? So we have order 1 already. That's why we increase k by 1. However, it's a while loop, right? When we increase k, now k becomes 1, and this k becomes 1. So now our r is supposed to be between 1 and n minus 1, right? Why? Because in order to have the expansion in 4 directions, right, your index r and c are not supposed to be at the corners, right? Look at this. Let's say you have 1 here and 0. Let's say r and c is 0 and 0. You are at in this index, right? And k is 0 at first. So you check this one, you find this is a 1. So you increase k by 1. Now you have order 1, right? And then your k, your r is supposed to be between 1 and n minus 1. Because if this is not the case, you can't expand to the left. This k guarantees that if there is another one to the left, basically, right? This k. So this guarantees that for an index r, if there is no, if the r is not more than k, which now becomes 1 after 1 iteration of this while loop, right? If this r is not more than 1, this means that there is no way there is another one to the left of this r and c. And similarly for this side, if you have a 1 here, and let's say r and c is, you're at this index, right? And this is 1, you have order 1 already, and you increase the k. And then if your r is not less than n minus 1, meaning if your r is not here and it's here, basically, you don't have anything to the right. That's why you can't expand anymore. So you need to kill the while loop immediately. So yeah, basically you start from k0. This is your r and c index itself. If R and C is not in a band, it means that it's 1, and because it's 1, you have order 1 already. You increase the K by 1. But next, your RNC is supposed to be in a location that you can expand in 4 directions. If you don't have this criteria and this criteria, you can't expand in basically right, left, bottom, and top when K becomes more than 0, right? As soon as K is 0, you're fine. You have order 1, no problem. But when K becomes 1, after the first iteration, your R cannot be at the corners or sides, right? Because this way, if you have a basically you have your index 1 is on the top side, you can expand upward. So you cannot increase your order more than 1 to become 2 because there is nothing above your index. Or for example, if your, let's say you have something like this, if your 1 is at this corner, right, bottom corner, right, although you can expand to top and left, you cannot expand to right and bottom, right? And there is no need to increase K if that's not the K, if that's not the case. So you already kill the while loop and move forward. That's what this while loop is doing, expanding in 4 directions. I hope this is clear. So I'm gonna run this on the test example. So this works on this test, but I don't think it's gonna work for the, probably we're gonna have time limit error now. Let's see. Yeah, time limit error, because like for large values it doesn't return, it doesn't work. The reason is that if you have n2 here, so like so far your order is n squared, right? And then you have this while loop that could get up to on, and you have basically a bunch of nested loops which makes the overall time complexity n cube, right? And apparently this one is not accepted for this problem. So I'm gonna try to improve the brute force method that we came up with, right? What we're gonna do is, if you think about it, if at each index uh, R and C, right? At each index R and C, if you know the longest basically wing to right, left, uh, bottom, and right, and up, basically. Let's say you have LR for right, LL for left, LU for up, and LB for bottom, right? If you knew LR, for example, is 3, LL is 2, let's say LU is 4, and this is, let's say, 1, right? This means that if you have a 1, you would have 3 more, sorry, 2 more ones to the right of it, right? This is LR3. You would have another one to left of it, which makes it LL2, and that's going to be tricky. You would have 4 ones to the top. So this, yeah, let me try to draw it. So you have 4 ones to the top, and you don't have any extra ones to the bottom. So this is basically L bottom equals to 1. So you have a thing like this. And what's going to be your order right now? It's 1, right? Basically the minimum of 4 of them. Does that make sense? So here, for this index, the order is 1, because we don't have anything extra at the bottom. So that's the idea we want to work with. If we could come up with a way that could tell us what's the length of ones in each directions at an index, then we could mean them and get that as an order for that specific index. And then we would look through all the grid points, basically in a 2D grid, and find the maximum of that order, basically. That's what we're going to do. In order to do that, what we can do is that we can use dynamic programming, right? The way it works is that we want to somehow improve this while loop we had in between. So if we get rid of this while loop, then our solution would be O(n) squared. And that's probably acceptable based on the solution tab, obviously. So the dynamic program is going to help us here to get rid of this while loop. How? It's going to basically, let me start the code and then we can talk as move forward. So we start a DP array, dynamic programming. It's a 2D array that basically is the same size as the original 2D array and 2D grid that we had, and it starts all with 0. Basically, it assumes for each index there is no 1 available at first. And what we want to do is that we want to see what at each index we have as the largest possible sign, plus sign. The way we do it is that we go from left to right. Let me copy and paste an example. So we go from left to right first. So we start from here to go to right, and if we see a 1, we increase that index in a DP by 1. Let's say here. So you go from left to right, 0, nothing. And if we see a 0, we don't do anything, right? 0 doesn't care, doesn't help us. So if we see a 1, the index of DP increases by 1, and we move forward basically until we get to a 0. For example, here, if this is 0, we don't need to do anything about it, right? Because if we have a 0, we don't have anything to start or plus sign basically. So we go, we get to the third row, right? This is 1, and we make DP 1, but this can be 2 because at this, from the left side, we have another 1 which makes this length 2 basically, and when we get here we make it 3. This means that in the DP array, so let's say this is the DP array, I keep this as original, right? In the DP array, if we move from left to right, we have 1, 1, 1, right? But for this index, the left wing is 3. That's why we have here. For this index, the left wing is 2, right? That's what we have here. And for this index, the left wing is 1 because we don't have anything. We don't have any more 1s to the left. That's why the index is 1. And we keep doing this from right to left now. We start here, we go right to left. We start here, right, left, 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 here. And then we get here, now this is 1, this is 2, and this is 3, right? Because we start from right to left. Now this is 1, this becomes 2, because to the right of this index, we have another 1, which makes this one 2, right? And then when we get here, we have 3. Similarly for all of them. We do top to bottom, right? We move from here, 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 and then here, here, here for each column. And what we get is that we start here, this is 0, 0, and we get 1. When we get 0, we don't care. 0 still stays 0, and then we move forward. The next column, we get here, we get 1. So this is 1, right? And we get here, this is 2. It increases to 2 because in the upward wing, we have 2 1s now instead of 1. And then we get here, we make this 3 because in the upward wing, we have 3 1s in the original array, right? That's why this index becomes 3. And we do the same for this one. And then finally, we go from bottom to top, right? We start from here, 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 here. And when we do this, we get something like this instead, finally. And now, basically, we have a DP. What we can do is that we can come up with basically 4 DPs, DP1, DP2, DP3, DP4, and then we combine them somehow to get for each index to get the minimum of the values of the 4 DPs we have. Or basically a smarter way would be to generate 1 DP, and once we are done with, for example, left to right move, we have an updated DP, right? And then when we are moving from right to left, for each index of the DB, we calculate that basically the longest wing, and then compare it with what we have in the DP, and then update the DP value if the current wing is less than the current DP value that we have. Let's jump into the code and you see it for yourself. It's much easier written. So we, let's say, move from left to right. So for the rows first, and we initialize a value counter for columns in left to right. Now we're doing left to right move. Okay, if R and C are in band, what we do is that the count is 0, right? Because if they are in a band means that the entry at index R and C is 0, so 0, we don't care about 0. However, if it's not 0, which means that it's 1, we increase the count by 1. And then what we do is that if we increase the count by 1, then we update the DP array to be count, right? Similar to what the example we see. For example, in this row, if we move from left to right, this is 0, we don't care. This is 1, we add 1 to count. Count now is 1, right? And then we update DP of RC to count. And then we get here, this we haven't encountered any 0, count gets 1 added to again. So now count is 2. Now this DP of RC becomes count, which is 2 now. And then finally here, the DP of RC becomes 3, which is the new count now. Now with this, our left to right movement is done. Now we restart count because we want to do right to left movement now. And for this, we need to restart everything. And then once we get to for each basically index R and C, we calculate this count and then compare with DP R and C. If the DP of R and C is larger than the count, which means that we have a wing that's represented by count is less than basically the value in DP and R and C. And because we are doing the minimum at the end, remember we had 4 wings, we want to do the minimum of them at the end, we replace the value of DP and RC with the new count basically. And it goes like this. You start from n minus 1 going backward. You start from last index going backward to the first index. And if this RNC is in band, again, it's pretty similar to the previous one, except for very small change here basically. What we do here is that we say if DP of R and C is larger than count, right? Update DP of R and C with count. Because if, so DP and R and C so far means the left wing, right? For index R and C. Meaning, for example, if DP and R and C is 3, means that at index R and C you have 2 extra ones to the left. However, this count now means from right wing, meaning that at DP at index R and C you have a value count, let's say it's 2. If the right wing is 2 and left wing is 3, we don't care about 3 in the left wing because the minimum is what we care about. That's why we update the value by count. Make sense? I hope it makes sense. So this is the end of or right to left basically move. Now what we do, we need to move from top to bottom and bottom to basically bottom to top basically. What we do is that now we do something like this, exactly similar idea. However, we change this R here with C because we're doing the column movement, and we initialize count to 0, and similarly if the same story in band count is 0, else count gets updated. And again, if DP R and C is larger than count, DP and DP of R and C becomes updated to count, because the count means that there is one wing which is less than the other already counted basically wings. We do it for basically the first one was from top to bottom. Now we are doing bottom to top. You see, it's like exactly same thing as the first iteration, except for a small caveat that we update DP, R, and C to count every time you're counting. Right now, our DP array is done, right? Because we started a DP array, we went left to right, and then we went right to left, and then we went top to bottom, and finally we went bottom to top. And then for each stop, for each direction, we updated DPR and C. And now the DPR and C includes the maximum, basically the largest plus sign of each index, right? And what we want to do is that we want to find the maximum value in DPR and C because that's the largest plus sign in the whole grid. For that, we do another nested for loop. We can make this one R and C to be consistent with what we had. And we compare the result with what we had so far, and then finally return result. What we do is that we goes over every component of DP array, and then we compare with the result. Let's say you start from first row of the DP. You get a value of 3 somewhere, and then you update the result to 3. But if you don't get any value more than 3 for the rest of the DP, you return 3 basically finally. However, if you get, for example, 5 at some places, you update the rest to value 5. So basically you choose the maximum value of your DP array at the end. Let's see what it does. Invalid syntax. I left count somewhere. Okay, this is 0. Sorry. Ooh. Is something wrong? Okay, I need to go do this. This is wrong for some reason. Let me check it out then. Okay, it seems like there was a typo in my code here. So I changed, it should have been F instead of 4. That's why it was not working. And then if you submit this, yeah, you remember that we got time limit exceeded for the brute force solution. If you submit this, yeah, it works 77%. Sounds good. All right, I hope you enjoyed watching this, and let me know if you have any question, anything clear, or any problem whatsoever. Just let me know. Have a good day.